So the next topic of discussion would be single mode fibers. So in the last few classes, we've been discussing the various modes in optical fibers, like specifically these LP modes, right? But previously we've discussed that if a fiber has many modes, like a multi-mode fiber, then intermodal dispersion is a big problem, right? So for most applications nowadays, actually single mode fibers are used, okay? Which means basically only the lowest order mode, which is the LP01 mode, right? That exists. So no other mode exists in these fibers, right? So yeah, so by single mode fibers we mean only the LP01 mode is guided. All higher order modes are not guided, right? So for example, we saw in a step index fiber, right? This means that the V number has to be less than this 2.404, right? Which is the first root of this Bessel zeroth order Bessel function J0, right? So if the V number is less than that, then only this fundamental mode exists, which has no cutoff, right? So for example, so the V number is inversely proportional to wavelength, right? So it goes, it's like k0 a times square root of n1 square minus n2 square. So k0 is 2 pi over lambda, right? So for a given fiber, right, there will be a range of wavelengths over which this condition will be satisfied, right? And for that range of wavelengths, it will act as a single mode fiber, right? So basically, for some range of wavelengths, so V has to be less than this number, and since V is inversely proportional to lambda, that means lambda has to be greater than some number. So this is known as the cutoff wavelength. Right, so basically the V number at this cutoff wavelength is basically equal to this 2.4, right? So as an example, there is this fiber known as SMF28E. Okay. So the claim to fame is like the most widely deployed fiber in the world. So for example, most of the internet traffic is going through these fibers. Right, so it's covering sort of the most terrestrial area in terms of the area covered by the fiber optic network. Most of that is this particular fiber. Okay, so it's made by Corning. So the parameters are, so core index is about 1.46, right, in glass. So the normalized refractive index contrast is in the 10 to the minus 3 range, right? So it's very small. Again, because we want, so also B is proportional to square root of this delta, right? So this has to be small. And then the core radius is also small, it's about 4 microns. Okay, so if you put in these parameters, you'll get the cutoff wavelength to be about 1250 nanometer. Okay, so basically for wavelengths longer than 1250 nanometer, it's single mode, right? So for example, in optical communication networks, right, the wavelengths which are used are typically sort of like from 1.3 to 1.65 in that range. Okay. So you can see for this range of wavelengths, this is a purely single mode fiber, right? So these are the telecom wavelengths. Okay, so then because this is the most widely kind of used fiber, it's good to know sort of some properties of single mode fibers, right? That's what we discussed. So first thing is, for example, we have this BB curve, right? So B is, remember, the normalized propagation constant, right? So to remind you, this is right. So we had this BB curve, right? So again, B is right. So for example, for a particular fiber, as I change wavelength, my effective index or propagation constant changes. Right? So, for example, for the lowest order LP01 mode, you know it looks something like this, right? And then at around 2.4048, the next mode starts, right? So this is LP01 and this is LP11, the next mode. Right, so below this, we have single mode, right? So this is sort of the range of operation of a single mode file. Okay. So if you look at these sort of range, so typically the V numbers we are looking at here are say between 1.5 up to 2.5, right, or 2.4. Okay, so in that region, there is a nice empirical formula for this BV curve that is very useful. Okay. So you write it like that. Okay, so instead of, so remember how we calculated this curve, how we plotted this curve is we took a particular V number, then solve the transcendental equation, found V, right? So for each point we had to do that. So there is no actually analytical formula for this curve for a step index fiber, right? But so in this range of operation for the fundamental mode, it can be empirically fit to this curve, and this is accurate to an error of less than 1%. Okay, so it works quite well. So A and B are some constants. So A is (1.14) and B is 0.26. Okay. So in this range, for the LP01 mode, this BB curve can be modeled with that equation. Okay. And we'll see. So, for example, we'll use this to calculate the dispersion in the fiber. Okay. So even single mode fibers, as we'll see, have some dispersion, right? Although they have no intermodal dispersion, they still have some dispersion, so you will get some pulse broadening. So we'll see where that comes from, and to calculate those things, these are useful. Okay. So the second thing is, so the mode profile, right? So for LP01, we know that so there is no azimuthal dependence. L is equal to 0, and basically the mode profile just looks like a spot, right? So looks like that, right? So it's like a Bessel function. So this is J0, right? And then in the cladding it's like K0, so something R, right? So it looks sort of like Gaussian, right? And again, so instead of using these Bessel functions, which are quite tedious to calculate things, right? The fundamental mode can be approximated by Gaussian. So Okay, so basically if we take the mode profile as just some e to the minus r square by w square. Okay. So now w here is known as the spot size, right? And how we estimate w, right? Of course, so w will depend on the fiber parameters, like for example the core size, the index difference, etc. Right? Because we know that these parameters, these functions depend on those parameters, right? So for any particular fiber, we have some fundamental mode, and we want to estimate if, like, what could be the Gaussian spot size for that, right? So the way we do it is basically we just take the overlap of this approximate Gaussian function with the exact Bessel function, right? So we take a mode overlap and see for which value of W the overlap is maximum, right? So that approximates the mode the best for which the overlap will be maximum. Right, so basically what we do is maximize this overlap integral. So we take the product of this Gaussian function with the radial profile of the mode, right? So we can do this for any fiber, right? So for example, if we take the step index fiber, then this R of R would be the Bessel function, K0. Right? But for example, we've also seen gradient index fibers, right, where the mode profiles would be different, right? So for example, in the square law, we saw that these were like the Laguerre functions. Right, so you could do this for any fiber as long as you can solve for the modes for that fiber, right? You can put that solution here. Then we normalize it with the sort of the integral for each function separately. Okay, so this quantity will be less than 1, right? Less than equal to 1. If this function is the same as this, then this will be equal to 1. Okay, so yeah, so for a step index fiber, for example, we put the Bessel function in here and then calculate for which W will maximize this, right? So of course, you can see that it will involve some mathematics. It's not a trivial thing to do, but people have done that, and basically they found this empirical formula, or sort of semi-analytical formula by maximizing this, that the spot size depends on the fiber parameters. So so the spot size as a ratio of the core size so it depends on the B parameter again. Okay. So given a fiber with some B parameter, right? So if you know the fiber parameters, core size, core and cladding index, we know the B parameter, we can find what is the Gaussian spot size for the fundamental. Right? So this is for step index fiber. Right, so again this is accurate. So this is valid in the range, again with B numbers between 0.8 and 2.5, right? So again, this exceeds the range covered by this. So it works for most applications. Again, error here is less than 1%. Okay. So this is for a step index fiber, right? Which is sort of again the most widely kind of used fiber. But as I said, you can do this for any kind of fiber, right? And so note that for the square law fiber, right? Remember the lowest order mode, right? So for the square law fiber, the lowest order mode was, I mean, we could say it as the LP01 or equivalently the TEM00 mode, right? And recall that the mode profile there actually came out to be exactly like a Gaussian. Okay. So for square law fiber, actually, it's the mode profile already R of R is actually exactly a Gaussian. Okay. So in that case, the spot size here, right? You can directly write like this in terms of the V number. Okay, and this is exact. There is no like maximization and approximation here. Here, because the mode profile is exactly Gaussian, this is an exact relation. Okay. For any other fiber, again, it won't be a Gaussian. Like for example, a linear profile or something. Again, you calculate what mode profile it will have, and then take this overlap, right, to calculate the mode size. But for the square law, it's exactly a Gaussian with that spot size. Yeah, so the question is basically this, right? So in the class we saw this formula, which was for a square law fiber, right? So that is exactly valid, but it's for a square law. For a step index, we have to use this formula, which is approximate, right? Because actually the fundamental mode is not a Gaussian, but it works well with less than 1% error. Okay. And why we want to do this is why we want to approximate the lowest order mode with the Gaussian is that calculating various things becomes much easier, right? Instead of using the Bessel function. So as an example, I think if you go back to that SMF28E fiber, which is the most widely used fiber, right? Okay, so there's a so W is the spot size, right? So that's sort of the half width you can see, right? So that's like where the field decays to sort of 1 over E, right? So what is typically quoted for fibers is known as a mode field diameter, which is twice of the spot size. Okay. So the mode field diameter for this SMF28E, so it's about 9 micron at 1310 nanometer and about 10 micron at 1550. Okay, so these wavelengths are important for optical communication systems again. So remember the core size. I just erased it, right? So the diameter of the core for this SMF28 is 8 microns. Okay, so you can see the mode field diameter is slightly bigger than the core. Right? It's 9 micron, 10 micron. Right, and because the field extends into the clad. Okay. So again, for example, what you can do is, if you use this Gaussian approximation for the lowest order mode, you can easily calculate, for example, what is the confinement factor, right? You can calculate what is the area under the curve in the core versus the total. You can do that much more easily with this. We had discussed the exact calculation with Bessel function and something, right? So that is quite complicated. But for the lowest order mode, you can use this Gaussian function and sort of easily evaluate, for example, the confinement factor. One other quantity which is often quoted, so apart from the mode field diameter, is the mode area. Okay, so this is an important parameter for various applications, like for example, also in nonlinear optics. So this mode area A effective is basically just pi w square, right? So w is the radius of the spot, so pi w square is mode area. So again, for this SMF28E, this comes out to be about 80 micron square at 1550. Okay, so just to give you some idea about the numbers involved. Right, again, so this is slightly larger than the area of the core itself, right? Again, because the mode sort of leads into the cloud. Okay, so as I said, this Gaussian approximation allows us to calculate some things quite easily, right? So let's look at one such thing, which is splice loss. Right, so a splice is a term that is used for a joint to connect two fibers. Okay, so you can imagine this needs to be done at various places, right? So you have one fiber coming from somewhere, and then another fiber coming from somewhere else, and you need to connect the two ends. Okay? You need to join these two fibers. So that procedure is called splicing, and the joint is called a splice. But of course, right, so if this joint, you can imagine, so we are talking about very small core sizes and node sizes here, right, microns. So you can imagine that the two fibers have to be aligned very, very precisely, right? So for the power to get transferred from one to the other efficiently without or with negligible loss. So what are the tolerances that are allowed? We can calculate again using this Gaussian approximation for the mode. Okay, so again, so idea is you have some fiber coming from somewhere, right? So this is one fiber. Okay, so it's going somewhere, connected to somewhere. Another fiber coming from this side. Okay, so the central region shows the core and then the cladding. Okay, and we want to connect these two fibers now. Okay, so usually how that's done is by using a tool known as a fusion splicer. Okay, so basically what you do is you sort of mount this end of the fiber. So first thing you have to do is cut this end of the fiber. This facet has to be really perpendicular, right? So this facet has to be exactly perpendicular. If this is not cut properly, right? So you can imagine, so if there is some roughness here, or if this is not particularly straight, if this is angled, then right, you'll have a lot of loss. So first thing to do is cut this straight perpendicular to the propagation axis, right? So that is known as sheaving. Okay, so these ends are known as sheaved facets. Okay, again, so there is like a proper tool for that, right, with a very sharp blade. So you can actually cut the fiber such that the facet is very smooth and perpendicular. Okay, so once you have these sheaved facets, then basically what you want to do is bring these fibers together and align the core, right? So you can imagine if this is offset, this is somewhere up, then if I send light from here, it will come out, right, and it will not couple into this fiber, right? So you can imagine it will be very sensitive to the alignment, right? Especially because again we are talking about these sizes to be like less than 10 micron, right, for single mode fibers. So basically what you do with this fusion splicer is you sort of mount these two fibers on two arms, and then you have very precise motion stages, right? Which sort of using which you can come and align these two, and then basically it generates an arc, okay, which basically bends sort of this region near the sort of joint, okay. So it raises the temperature to above the melting point of glass. So basically the glass sort of in this region sort of starts flowing, and then basically these two things are joined. Okay. So this ends up sort of becoming one joint on one side. Okay. So yeah, something like. Okay, and so this joint is known as a splice. Okay, so again, basically we want to know what is the tolerance on this misalignment that we can have, right? So again, you can imagine for fibers laid over hundreds and thousands of kilometers, we want to do this at various places, right? There will be a lot of these splice joints happening at multiple places. Also, sometimes there's a fault somewhere in the fiber, right? So you have to sort of cut and replace that part of the fiber. So this needs to be done very often at many places, right? So basically we want to do this very efficiently without much loss at all. So we can estimate the loss that we get due to misalignment by using the Gaussian approximation again. Okay, so basically, let's say sort of the misalignment. So that, okay, first of all, there could be two kinds of misalignment, right? One is just a transverse misalignment, okay, so where this is shifted up, for example, with respect to this fiber, right? But the facets are sort of parallel. Okay, so this would be transverse misalignment. You could also have angular misalignment, right? So which means basically this is at a slight angle. Right, so the facets are not parallel, but they are at some angle theta. So again, you can imagine the coupling won't be efficient because the light coming out, the mode coming out from this will travel straight, but then it needs to go at an angle to go. Okay? So this is angular misalignment. Okay, so basically we want to find out. So for some transverse misalignment u, so the cores are displaced with respect to each other by some distance u, or if the angle is not parallel but at some angle theta which is not zero, how does this affect sort of the power coupled from one fiber to the other, right? Or basically the loss that we encounter at this joint. Okay, so for this transverse misalignment, right, so again, basically what we can do is, so let's say this is fiber 1, this is fiber 2, so this has some mode here, this also has some mode here. Again, we are looking at the fundamental mode, right? So, so we can assume or we can approximate them by Gaussians, right? So we could, in general, assume these are not two identical fibers, but let's say they could be slightly different fibers with slightly different V numbers, right? Which means the spot size here is W1 and here is W2, right? Which could be different from each other. So basically the mode in fiber 1, okay, so what we say is that the direction in which the misalignment is happening, let's call that direction x, Okay. Okay, and then the other transverse coordinate we can call y, and then the propagation direction is z. Okay, so then the mode in fiber 1, it's easier to do this in Cartesian coordinates, right? Because basically the misalignment is happening in one particular Cartesian direction. So the mode here in fiber 1 we write as, again, this Gaussian function. So r square we write as x square plus y square. Spot size is w1. Okay, and this is normalization such that basically the integral of psi square over the xy plane is 1. Okay, and then the mode in the second fiber, again we can approximate by the Gaussian. Let's say it has a different spot size w2, and now this is displaced by u, right? So the center of this is displaced by u in the x direction. So here I write x minus u square. Okay, and y is still y. So basically we can write the mode profiles of the guided modes in the two fibers like this. Okay, and then how much power is coupled, say from 1 to 2, would depend on the overlap between these two again, right? So yeah, so these are normalized such that right, this integral is 1. So basically the fractional power which is coupled from, let's say, fiber 1 to fiber 2, or the transmission coefficient, right, from here to here, is just square of the mode overlap right. So whenever, I mean, we've used this mode overlap in various places, right? So for example, we said that, okay, at the input of the fiber, we come from free space and we focus down with some mode profile, right? What mode will be launched depends on the mode profile, right? So here it's something like that. So for this fiber, the input launch profile is the mode of this fiber. Okay, so since these are Gaussian functions, this integral is quite straightforward to evaluate, right? You just have integrals of Gaussian functions. So you have standard integrals that can easily evaluate. So you can do this yourself and check that this comes out to be okay. So this transmission coefficient is also now a function of, it looks like a Gaussian function of the misalignment u. Right, so again you can imagine if we, instead of taking the Gaussian function, we took the actual Bessel function, then this integral would be very difficult to evaluate and you would actually require numerical integration to do it, right? So that's why again this Gaussian approximation is very useful. Okay, so you can see, of course, that as u increases, this transmission goes down, which means the loss increases, right? Of course, as u increases, the loss increases, transmission goes down, right? And the transmission goes down quite fast, right? It's like a Gaussian function. So for a given pair of fibers 1 and 2, you can see, of course, the maximum transmission happens for u equal to 0, which means the fibers are perfectly aligned, right? The cores are centered. So maximum transmission is basically at u equal to 0, right? And you can see that depends on the two spot sizes. Okay. You can see that this is 1 if W1 is equal to W, right? If the fibers are identical, then you get 100% transmission, no loss for perfect alignment, which you would expect, right? So then it looks like one fiber. No misalignment, identical fibers, it just looks like one fiber. So of course, you should have 0 loss. How are we accounting for the gap? So there is no gap, right? So I mean, you could also take into account the gap, but as I said, when we splice, what actually happens is that you actually sort of join these two ends using that arc. Okay, so basically the two ends are now touching each other. There is no gap. But you could also take a gap if you want, right? But that is not a very practical case because usually the two ends are not left like hanging like that. Okay. So as I said, in the fusion splicer, when we splice means that it's now fused joint. But you could, like, for example, in the book there's a section which actually calculates, so you have some distance d here. Then what basically you need to do is the mode coming out here will diffract, right? So you need to take into account how much this diffracts out and then take the overlap with the mode in the other side. Okay, so you could do that, you could calculate it. But as I said, it's not a very practical case, and also turns out that it's not very sensitive to this distance d here. Okay. So as I said, for once you slice it, basically the distance is 0 anyway. But anyway, you can even just by sort of naked eye, you can get it quite close within like a few microns or tens of microns, and for that those distances the beam doesn't diffract much and it's not much of an issue. So longitudinal misalignment is not really relevant, so we won't discuss it, but if you are interested in how to calculate that, you can look at the book. Anyway, yeah. So usually again we measure losses in dB, right? Just like for example the fiber propagation loss, we used to measure dB per kilometer. So here also for each joint, usually the loss is put in dB, right? So the splice loss would be some alpha in dB. Basically, you take the 10 log of this, right? So okay, so for example, if you look at how the splice loss depends on this ratio of the mode field diameters of the two fibers, right? Okay, so it goes something like that. So the loss is 0, of course, when W1 is equal to W, right? And as you start deviating, the loss goes up. Okay. and you can see that if the difference in spot size is twice, right? So either W2 is 2 times W1 and W1 is 2 times W2, then the loss is about 2 dB. Okay, so that's quite a big loss. So you can imagine you have like hundreds of thousands of these splices over the fiber link, right? So that could give a huge loss. So typically a figure of merit is that you want splice loss less than 0.1 dB. Okay? So for each joint, you want the loss to be less than 0.1 dB because you have many of them. So you can put 0.1 here, and you'll get that. So the spot sizes have to be within 14% of each other. Okay. To satisfy this. So, but as I said, mostly these two would be identical. Right? As I said, for example, in most of the communication network, this SMF28E fiber is used, and so basically you're joining this two ends of the same fiber. Okay, so W1 will be equal to W2. Right, so this was for perfect alignment. Now let's consider the case. So let's say now the two fibers are identical, right? So which is usually the case. So for identical fibers, the same spot size, then so here if you put W1 equal to W2, then as a function of the misalignment, we get this to be e to the minus u square by W square. So this is again a Gaussian function in U, the misalignment. Right? So the transmission goes down like that with U, right? Again, if you want to denote the loss in dB, then you take n log 10 of that. So you get, okay. So the loss in dB scales with U over W square. Okay, so the splice loss in dB versus U goes like that. Right, so again to get an idea of some numbers, so again for this SMF28E fiber, so the spot size, as we said, was about 5 micron at 1550 nanometer. Okay, so then if you want splice loss less than 0.1 dB, the misalignment should be less than 0.76 micron. So you can see that there's a very high tolerance or very low tolerance, that, right? So compared to the spot size, the misalignment has to be much smaller. Right? So this is less than a micron. So really your alignment has to be almost perfect for the joint video. So again, this shows that transverse alignment is very, very critical. You need at the very least sub-micron precision in your, for example, fusion splicer to align these two. Okay. Why initially it decreases the loss? I guess you're talking about this curve. Right, so again recall this here is a function of, we're plotting with the ratio of W1 and W2. Right? So the loss is minimum when W1 is equal to W2. Right? So on this side and this side, so on this side W2 is bigger than W1, and on this side W1 is bigger than W2. Okay, and basically, so 0.5 here is the same as 2 here, right? We are just sort of swapping these two fibers. So the loss value will be the same for W1 by W2 equal to X or 1 by X. Okay. Because, and so why we get loss is because the mode profiles are not same, right? W1 is not equal to W2. So even for U equal to 0, this mode overlap will not be 1. Right? So that's why the loss increases on both sides. So it's not that this x-axis is not increasing from here to here, right? This x-axis is just the asymmetry between the two fibers. Okay, so that's transverse misalignment. The other type of misalignment could be the angular one. Okay, so like this. Of course, this is highly exaggerated. Right? Typically, the angles will be really small, and they need to be really small. Right? You'll see that it's very sensitive. So again, you can use like a Gaussian approximation, but now you'll have to sort of. So for this, you can imagine because the z-axis is now tilted at an angle theta. Okay. So basically, right, or the x and y x-axis now becomes tilted with respect to x-axis of this one. So you can write, so this node here will be Gaussian in these coordinates. You can define a new coordinate here like x prime, z prime, y prime. Write the mode in terms of that, right, and then write x prime in terms of x, and then evaluate this integral. Okay, so it becomes a little bit more complicated. We won't go through all the steps, but there's I think a discussion in the book if you want to know more details on how this is evaluated. Right, so now let's consider again identical fibers, which is usually the case. Okay, so spot size here and here is the same W. Okay, so for this angular misalignment, the splice loss dB comes out to be again this factor of 4.34 because you'll get something like a Gaussian function again, right? So for the transverse misalignment, remember we had something like this, and then when we took the 10 log 10, we got 4.34. Similarly, you will have here. When you take the log, you get 4.34. Okay. So the theta, the angular misalignment comes in here, right? So here theta is in radians. Okay, so now the wavelength also factors in, right? Along with the spot size. So a ratio of the spot size to the wavelength is important here. And this N1 is basically, so to do the calculation, you have to assume some refractive index of the medium in between here, right? This sort of gap here. But as I said, so in the splicer, basically you fuse it, right? So basically this in between region also just becomes glass. So we can just use the refractive index of the fiber for that. Okay, so this is actually the refractive index of region in between. But for a splice, that's just the glass refractive index. Okay, so again as theta goes up, the loss goes up, right? So again, let's say we have this SMF 28E fiber. So again, the spot size is 5 micron at 1550. Right, N1 again is about 1.46. So again, if you want splice loss less than 0.1 dB, this theta, put in the numbers here, you can see has to be less than 0.6 degrees. Okay, so it's a really small angle you can see here. Right, this has to be basically almost parallel. Okay. Right, so you can see that both the transverse offset has to be very small, and this angle, so the angle between the two facets also has to be extremely small. Basically, it has to be almost, facets have to be almost parallel, and the chords have to be almost aligned compared to the spot size, right? In order to achieve low loss. But nowadays, the commercial fusion splicers can achieve these tolerances, and typically splice losses that you get are about, like, say, 0.1 dB per slice. So if we have both the transverse misalignment and angular misalignment, right, which would be a general case, right, of course. Okay, we just consider them as independent losses, and we can just add them up. Okay, so the total splice loss so from the transverse misalignment, we get this U over W, so we use the misalignment, right? And then from the angular, we get this. Okay, so you can see that the dependencies of these two, for example, on the spot size is opposite. Okay, so for example, if I go to a fiber with a higher spot size, then the transverse, for the same transverse misalignment, the transverse misalignment loss goes down, but the angular misalignment loss for the same angular misalignment will go up. Okay, so they have complementary dependence on the spot size W. Okay, so you can imagine that for a given transverse misalignment and angular misalignment that you can get, right? Let's say your splicer is accurate up to only some, let's say a transverse misalignment of, I don't know, 0.5 micron, and an angular misalignment of, let's say, 0.5 degree. Then you can sort of, from this formula, you can calculate an optimum W, right? An optimum spot size which minimizes the loss. Because one goes up with spot size, the other goes down. So depending on, for example, your splicer tolerances, you can choose a fiber with the parameters that minimizes the loss. Okay, so for example, if you plot the loss sort of in terms of these two parameters, so on one axis we plot the transverse misalignment. Okay. And on the other, this angular misalignment. Okay, so for each point on this 2D plane is for a particular transverse misalignment and a particular angular misalignment. Okay, so that will give me a particular loss value. So if I draw sort of constant loss contours, okay, so they look like this. Okay, so for example, this is the loss contour for 0.1 dB loss. Okay, so all points on this curve give me 0.1 dB loss. Right, so you can see either I could have high angular misalignment but very low transverse misalignment, or I could have relatively high transverse misalignment but low angular misalignment. Okay. So because there's a trade-off. So, and this is for 0.2 dB, this is for 0.5 dB. Okay, so again, for the specs we want to achieve, we want to lie in this range. Right? So the angular, so the tolerance of the splicer I'm using, the angular tolerance and the transverse alignment tolerance better be in this range, right? If it's more than that, then I have high loss. Okay. And yeah, one final thing to say is that, so this we calculated a splice loss, but this same calculation can be used to find the coupling loss, right? So for example, we have a laser which is giving out light in free space, and we want to couple it into a fiber, right? So typically we use some lens combination or something, we focus it down at the fiber facet, right? So you can imagine here you have some Gaussian spot, okay? And the fiber has some mode, which the fundamental mode can again be approximated as a Gaussian. And now again you have these two sort of misalignments, right? So where the focal spot is compared to the center, the core here, so there could be some transverse misalignment. And again, so the propagation axis of the laser is this, and then the propagation axis of the fiber, if it's at some angle theta, that will give me an angular misalignment. Okay, so by using the same formula, because again it's an overlap of Gaussian functions exactly, right? Same thing we did. So this same splice loss formula can also be used to calculate this coupling loss that we get. Yeah, so that's why this sort of Gaussian approximation is very useful. Okay, we've already exceeded time. Can you explain? Okay, question about quiz and majors. No, yeah. So for the upcoming exams, the material which is already covered for previous exam won't be repeated. So, for example, for the next quiz will be material starting from today. And explain physically the lambda dependence. Right, so if you remember this pi w over lambda, this is coming from, I don't know if you have a basic optics course. So if you have a free space beam, right, of spot size w and at wavelength lambda, it diffracts, right? And basically the angle of diffraction here, okay, is sort of given by this. The angle at which the beam diffracts is sort of given by this lambda over pi w. Okay. So you can see it's a ratio of the misalignment angle to the diffraction angle. Right. So if the misalignment angle is smaller than the diffraction angle, right? So basically, what it's saying is that anyway the beam is spreading, or the beam is composed of k vectors which exceed the misalignment angle. Okay, so it will couple well into the fiber and your loss will be low. But if the misalignment angle is more than this angle of diffraction, or the basically the angular k vectors present in your beam, then loss will be more, right? So that's why it's coming.